Let's use VSEPR theory to predict the structure of this molecule, so phosphorus pentachloride. So the first thing we need to do is draw a dot structure to show our valence electrons. We find phosphorus in group 5, so 5 valence electrons. Chlorine in group 7, so 7 valence electrons, and I have 5 of them. So 7 times 5 is 35, plus 5 gives us a total of 40 valence electrons that we need to show in our dot structure. So phosphorus goes in the center because it is not as electronegative as chlorine, and we have 5 chlorines. So we go ahead and put our 5 chlorines around our central phosphorus atom like that. If we see how many valence electrons we've drawn so far, this would be 2, 4, 6, 8, and 10. So 40 minus 10 gives us 30 valence electrons left over. And remember, you start putting those leftover electrons on your terminal atoms. So we're going to put those on the chlorines. And each chlorine is going to follow the octet rule. So that means each chlorine needs 6 more electrons. And so now each chlorine is surrounded by 8 valence electrons like that. So if I'm adding 6 more electrons to 5 atoms, 6 times 5 is 30, and so I have now represented all of my valence electrons on my dot structure. Notice that phosphorus is exceeding the octet rule here, right? There are 10 valence electrons around phosphorus, and it's okay for phosphorus to do that because it's in period 3 on the periodic table. I like to think about formal charge, and so if you assign a formal charge to phosphorus, you'll see it has a formal charge of 0, and that helps to explain, for me anyway, the resulting dot structure. So now step 2, we're going to count the number of electron clouds that surround our central atom. Remember, an electron cloud is just a region of electron density. All right, so I could think about these bonding electrons in here as a region of electron density around my central atom. I could think about these bonding electrons too. So here's another electron cloud, and you can see we have a total of 5 electron clouds around our central atom. The next step is to predict the geometry of the electron clouds, and those electrons, those valence shell electrons, are going to repel each other, right? So that's VSEPR theory, valence shell electron pair repulsion. Since they're all negatively charged, they're going to repel and try to get as far away from each other as they possibly can in space. And so when you have 5 electron pairs, it turns out the furthest they can get away from each other in space is a shape called a trigonal bipyramidal shape. So let me see if I can draw our molecule in that shape. We're going to have our phosphorus in the center, and we're going to have 3 chlorines on the same plane. So let me attempt to show 3 chlorines on the same plane here. These are called the equatorial positions because they're kind of like along the equator, if you will. So 3 chlorines in the same plane, 1 chlorine above the plane, and 1 chlorine below the plane. Those are called axial positions. All right, so there's a quick sketch. Let me see if I can draw a slightly better shape of a trigonal bipyramidal shape here. So let me see if I can draw one over here so you can see what it looks like a little bit better. So we could have one pyramid looking something like that, and then down here, let's see if we can draw another pyramid in here like that. So that's a rough drawing, but we're trying to go for a trigonal bipyramidal shape here. So let's focus in on those chlorines that are on the same plane first. So if I'm looking at these 3 chlorines, right, and I go over here to my trigonal bipyramidal shape, you could think about those 3 chlorines as being at these corners here. So it's a little bit easier to see they're in the same plane. So those are the equatorial chlorines. When I think about the bond angle for those, right, so those chlorines being in the same plane, right, you have these 3 bond angles here. And so when we did trigonal planar, right, we talked about 360 degrees divided by 3 giving us a bond angle of 120 degrees. So you could think about that as being a bond angle of 120. All right, so same idea, those bonding electrons are going to repel each other. When we focus in on our axial chlorines, right, so this one up here and this one down here, you could think about those as being here and here on your trigonal bipyramidal shape like that. And if you draw the axis, right, if you draw like a line down this way, Right? Connecting those, it's easy to see those are 180 degrees from each other. So you could think about a bond angle of 180 degrees between your chlorines like that. And then finally, if we think about the bond angle between, let's say, this axial chlorine up here at the top, right, and then one of these green chlorines right here, I think it's a little bit easier to see that's 90 degrees here. So this bond angle right here would be 90 degrees. And so those are your ideal bond angles for a trigonal bipyramidal situation here. It's important to understand this trigonal bipyramidal shape because all of the 5 electron cloud drawings that we're going to do, right, are going to have the electron clouds want to take this shape. So it's important to understand those positions. All right, so for step 4, ignore any lone pairs and predict the geometry of the molecule. Well, there are no lone pairs on our central phosphorus, so the electron clouds take a trigonal bipyramidal shape, and so does the molecule. Let's go ahead and do another example. So sulfur tetrafluoride here. So we're going to start by drawing the dot structure, and we need to count our valence electrons, of course. So sulfur is in group 6, so 6 valence electrons. Fluorine is in group 7, so 7 valence electrons. I have 4 of them. 7 times 4 is 28. 28 plus 6 is 34 valence electrons. We know sulfur is going to go in the center because fluorine is much more electronegative, so we put sulfur in the center here. We know sulfur is bonded to 4 fluorines, so we put our fluorines around like that. And let's see how many valence electrons we've shown so far. 2, 4, 6, and 8. So 34 minus 8 gives us 26 valence electrons we still need to account for on our dot structure. We're going to start by putting those leftover electrons on our terminal atoms, which are our fluorines. Fluorine is going to have an octet of electrons around it. Therefore, each fluorine needs 6, since each fluorine already has 2 around it. So we go ahead and put 6 valence electrons around each one of our fluorine atoms. All right, so we are showing 6 more valence electrons on 4 atoms. 6 times 4 is 24. So 26 minus 24 gives us 2 leftover valence electrons. And remember your rules for drawing dot structures. When you get some leftover electrons, you're going to go ahead and put them on your central atom now. So we have a lone pair of electrons on our sulfur. And by adding that lone pair of electrons to our sulfur, the sulfur now exceeds the octet rule. But once again, it's okay for sulfur to have an expanded valence shell. It's in period 3 on our periodic table. And once again, I like to think about formal charge, and if you assign a formal charge to that sulfur, it has a formal charge of 0, so that just helps me understand these dot structures a little bit better. So we've drawn our dot structure. Let's go back up and remind ourselves of the next step here. So once you complete step 1, next is the electron cloud step, right? So how many electron clouds do you have surrounding your central atom? So we go back down, and we look at our electron clouds that surround our central atom here, so regions of electron density. So we know that these bonding electrons here, right, that would be 1 electron cloud. Same with these bonding electrons, same with these bonding electrons, and same with these bonding electrons. And then we have a lone pair of electrons on our sulfur. Well, that's also a region of electron density surrounding our central atom. So that lone pair you could think of as being an electron cloud as well. And so we have 5 electron clouds, so just like in the previous example. And when you have 5 electron clouds, those electron clouds are going to try to adopt a trigonal bipyramidal shape, just like we saw again in the previous example. So let's go ahead and draw 2 possible versions of the dot structure for this molecule. All right, so I'm gonna draw one right here, and for this first version, I'm going to show the lone pair of electrons on the sulfur in the equatorial position here. So I'm gonna put the lone pair of electrons right here, right equatorial here, and so that means there are 2 fluorines also equatorial, and then that means that there's 1 fluorine here axial, another fluorine here axial. So that is one possible dot structure. The other possibility would be, of course, to put the lone pair of electrons in the axial position. So if we do that, we would have a sulfur bonded to 3 fluorines. Those would be the equatorial fluorines. And then we would have a lone pair of electrons, let's just put it right here in the axial position, and then another fluorine in the axial position. So here are our 2 possibilities. So let's see if we can analyze this structure. Now, when you have lone pairs of electrons in your dot structure, lone pairs take up more space, or non-bonding electrons, I should say, take up more space than bonding electrons. And so since they take up more space, they're going to repel a little bit more. And so that means that when you're trying to figure out valence shell electron pair repulsion, the lone pairs of electrons are more important to focus in terms of where you're going to put them. And so let's focus in on those lone pairs of electrons, and let's think about how they're going to repel the other electrons in these two dot structures. And so let's look at the left here, where we have the lone pair of electrons in the equatorial position here. And if you're thinking about how they're interacting with, let's say, these bonding electrons in the same plane here, this is about 120 degrees between the bonding electrons and the non-bonding electrons. And it turns out that 120 degrees is not as important in terms of repelling as, say, something like 90 degrees. So you tend to ignore the 120 degree interactions when you're analyzing these structures. However, a 90 degree angle between a bonding pair and a non-bonding pair, we have that example for, let me go ahead and show you right here. So let's think about this lone pair of electrons, right, repelling these bonding electrons, so in the axial position. Well, these two are only 90 degrees away, so remember, 90 degrees, of course, being closer, you're going to get more repulsion from this interaction than in the previous interaction. So we're going to focus in on the 90 degree interactions here. So those bonding electrons and non-bonding electrons repel each other, and you have one possibility, right, with the axial fluorine. You also have another possibility with this axial fluorine. So you have essentially you have a lone pair of electrons 90 degrees from two pairs of bonding electrons from the example on the left. And of course, that's going to destabilize it somewhat. But let's compare this dot structure with the one on the right now. So the one on the right, all right, so we have our lone pair of electrons in the axial position this time, and you can see that we have three fluorines in the equatorial position. So you have these bonding electrons in the equatorial position, which means that that lone pair of electrons is 90 degrees to all three of those. And so that, of course, is going to cause some serious repulsion. So 90 degrees to 3. And so you have, in the example on the right, you have these 3 interactions, 90 degrees. And the example on the left, you have only 2 of these. And so the goal, of course, is to minimize electron pair repulsion. So VSEPR theory actually predicts that this dot structure on the left is the correct one. And so you're going to see in the next video that non-bonding electrons are placed in equatorial positions in trigonal bipyramids to minimize electron pair repulsion. So just think about putting your lone pairs of electrons in the equatorial position. So the structure on the left wins, so let's go ahead and redraw that so we can analyze it a little bit better. All right, so I have my sulfur in the center here. Let's go ahead and change colors. So I'm going to put the sulfur in the center. All right, I have my fluorine in a plane, another fluorine in a plane, my lone pair of electrons in a plane. All right, so those are my equatorial ones. I have a fluorine this way and I have a fluorine that way. So when you're looking at bond angles, right, of course, between this fluorine-sulfur fluorine bond angle, the ideal bond angle anyway would be 120 degrees, right? So we can say we would expect it to be 120 degrees. If you're talking about this axial fluorine and this equatorial one, we know we would expect that to be 90 degrees. And then finally, between the two axial fluorines, right, so this bond angle back here would of course be 180 degrees. Okay, so we've done a lot of talking, and we still haven't even talked about the final name for the shape of this molecule, right? So let's go back up here and look at our rules really fast. All right, so we've done a lot of work to predict the geometry of the electron clouds around the central atom and draw it. And finally, we get to predict the shape of the molecule, and we do that by ignoring any lone pairs. And so let's go ahead and do that. So we're going to ignore the lone pair of electrons on the sulfur when we're talking about the shape. So if we ignore the lone pair and we actually turn this molecule on its side, so let's go ahead and do that. We're going to put our sulfur here. If we turn it on its side, the axial fluorines would now be horizontal. So those are so now it's horizontal like that. So I'll go ahead and put in so these are what the two fluorines that used to be axial there, and my two fluorines that were equatorial. they would look something like this, and it helps if you actually build this molecule with a molymod set. So that would be what the molecule kind of looks like here. And we call this a seesaw shape, right? So this is a seesaw shape or geometry. And let's think about why, right? So if you've ever been on a playground and used a seesaw, I'm going to draw a little kid here on one side of our seesaw like that. And so if the little kid puts his weight on this side, of course this side of the seesaw would go down, right? And then this side of the seesaw would go up. So just a little bit of intuition as to why you would call this a seesaw shape. All right, so I think we'll have to stop there, and the next video we'll do two more examples of molecules and ions that have 5 electron clouds.